guys, welcome back. So let's review a few concepts we learned in last lecture. We learned about interference of light. We also learned about thin film interference. We also looked at transmission and reflection grating, right? So out of those, let's look at the more key point. So we looked at this here, thin film interference occurs when there is one reflective phase change, then the object would be bright, right? Like, so the maxima will occur when we have this condition made where 2 times t equal to m plus half lambda dash, where t is the thickness of the phase, right? The light entering through the boundary. In this case, it would be the thickness of a bubble, so the layer, okay? A thickness of that. Thin film interference minima occurs if there is only one reflective phase change, and then 2t equal to m times lambda dash. Again, remember this lambda dash is a wavelength of a light in a material, okay, not in the vacuum. So lambda dash is again wavelength of the light in a material. Okay, so we also looked at sorry, this is not what I need to show you. I need to show you guys just a moment. I'm going to write this one. So we also looked at Young's double slit experiment, right? Young's double slit experiment, and we found condition, right? We found the condition for bright fringe to occur is what? D sine theta equal to m times lambda, right? So this is one of the condition, and then after using small angle approximation, we found here sine theta was basically L by Ym, so sine theta we wrote it equal to what? L by Ym, and then we found the other way, y by Lm. M by L, and then we found D equal to m lambda L by Ym, right? So remember, this D is the distance between the slit, right? This is a double slit, and Ym is the position of the maxima, okay? This condition is for maxima, right? Maxima, okay? So now one thing I just I noticed, so D equal to m lambda L divided by Ym. So this is for a condition for maxima. If we have a minima, this m would be what? We would replace m by m plus half, right? And times lambda, that would give us the minima. We also looked at a fringe spacing, and then fringe spacing is given by delta y. Basically, we just looked at this equation, and we looked at what? In place of, we looked at equation for Ym, we also looked at equation for m plus 1, and then we just got the difference between these two equations, and we ended up with Ym equal to lambda L by D, okay? So that was the fringe spacing lambda L by D. What else should we talk? Those are the most important thing. Those are the key points. The key points to take away from last lecture. So for today's lecture, we are going to talk about ray model. Okay. Ray model of light. Okay, so since we are talking about the light, so this ray model of light. So last time we talked about wave model of light, right? That is one of the model for description of light. Okay. Now we will start. Today we will start ray model of light. So let's look at, well, last time we were saying it travels like a wave. Now we are going to say it travels like a ray. Yes, that's what we are going to say. Okay. So why we could use ray model is basically, so maybe you're wondering, okay, what does that ray means? Ray means, you know, just the bundle of light coming from the source. Basically the source of light could be, you know, flashlight or laser pointer, or all of those could be in a bundle of rays of light coming from the source. Or, you know, light bulb in the room, that could also be, we could also talk about ray model for that as well. Now what does ray model do is, number one thing is assumption here is it ignores diffraction, meaning here in whenever we talk about ray model we say, okay, we are not concerned about diffraction at all, so ignore diffraction. Diffraction of light, remember, because last time we saw that if we allow a light to pass through very narrow opening, it travels like a wave. Basically we saw the bending of a light that happens as you know, that we call it as a diffraction. Okay, now here we will ignore a diffraction because for ray model, so diffraction, when we're talking about the diffraction, we're talking about the slit space is basically really tiny, about like 0.5 or half micrometer. Okay, so that's but then for ray model most of the slit would be about 1 millimeter. For diffraction we had about, this was about 0.5 micrometer. Okay, so this is, you know, the slit we would be, you know, using, at least for ray model, is it would be somewhere around 1 millimeter or bigger, so it's okay. So we don't have to talk about, we can ignore the diffraction pattern of light. Okay, so a ray model, basically this is one of the most important assumption here. Ray model also says that light that travels in a straight line. It also says that light, if we let the source of, if we light, if we have a source of light, and then this light keeps traveling until it interacts with any other medium. For example, right now I have light here. If I bring this aquarium here and then place it here, the light is going to keep traveling until it reaches the water there. Or maybe if I have a closed aquarium, probably it touches the glass, and then it's going to interact with that glass, and then travel again, it's going to interact with another material inside. Okay, so those are some of the assumptions for ray model. Have you guys wondered how do you see your image on a mirror? Like, how do you see your image? You go in front of the mirror, you stand there, boom, right there is your image. If you go a little bit further away, your image also goes further away, right? You see a person inside the mirror, but that's image. Okay, so the object, so in that case, let's say object, you stand in front of the mirror, you would be the object. Okay, and then there is the image of your body is formed over there on the on the mirror, and that's the image we call image. Okay, so it turns out that based on the principle, it turns out that the image formed on a mirror has to do with something called reflection of light. Okay, so reflection of light is like this. Light goes, let's say, even just here. Okay, I'm just gonna give you guys an example here. So light travels like this, gets here, but then now because this surface is like opaque, right, like so it cannot penetrate further down. So what happens, once it reaches there, it has to turn back, it has to come back to the original medium. So we call that phenomena as a reflection of light. Okay, so reflection of light. So basically I'm gonna just draw this media here. Let's call this as some medium. Okay, some medium meaning this is a material with different property. It could be also air, it could be vacuum, it could be glass, it could be other things. Okay, so but whenever we talk about light, we are kind of mostly talking about the transparent medium, because we need to be able to see, right, what's happening. So let's say this is some transparent medium we have here. So let's say, to talk about the reflection of light, what happens is light goes down. So this is how we represent. If we had a light bulb here, I would say that okay, the light is coming like this from this. It goes down. This is some plate. Okay, so it goes. This is the. Let us call this. I'm just going to call it some medium. Okay, and then I'll put this arrow to say that light is going in that direction. But because let's say to have a reflection, this is important, this is some medium, so let's say this is completely opaque, meaning the light cannot penetrate here. Okay, so let's say this is a medium opaque. Okay, so what happens is this light cannot enter through this boundary, so it has to go back to its to the medium it came through. So it's going to go back, the light comes here, touches the boundary, and then it's going to go back to the same medium it came through. Okay, so this kind of phenomena is called a reflection of light. So where do we use this? Like in day-to-day life, there are various examples. Mirror is like where you look at your image, right? So you see that is actually formed due to the reflection of light. Details of it is given very well in a textbook, so I want you guys to look at that about the reflection through plane mirror. We'll also talk about, there is also another type of reflection, that's through spherical mirror, and that's what I'm going to talk about today here. Okay, so reflection through plane mirror. Oh, sorry, not plane mirror, spherical mirror. Again, let me write this down here again. Reflection, okay, F-L-E-C-T-I-O, and this is important because after, later on in this lecture we'll also talk about another phenomenon called refraction, but for now let's look at reflection. Okay. So reflection through spherical mirror. Let's say, what are the example of spherical mirror? Some of the example is like, your rear view mirror on your car. Some of these is with this. I have a spoon here, right? So if you look at this here, see, maybe you guys can see the image of camera there. I have my camera there. Okay, so let's see. You can also see, right? Like, so let's look at this. I don't know, now let me see how big is. Okay, so that is the mirror. You can also see this side. Okay, so this one, this is one type of spherical mirror. This part forms the another type of spherical mirror. You see my, maybe, let us see. This is kind of harder to see. Okay, this is easier to see. Okay. Oops. So people had actually mirror in even ancient time also. So if you look at here, so ancient optical instrument would be like, early mirror would have been made of polished stone here, maybe copper or bronze. Okay, so there is also another mirror that was found among the artifacts found in pyramids. Among the artifacts found in pyramids, it was around 1900 BC, so it looks like bronze mirror. Let me this other part of about how to draw this ray diagram for mirror is going to take some time, so I'm going to make that separate video. Okay, so we'll continue spherical mirror in next video.